Okay, hello and welcome to a lecture from my office. Had to get out of the house, and so I am recording this week's lecture from my office at SAIC. Anyway, so this week we are talking about the atmosphere. So we've talked about the hydrosphere, we've talked about the biosphere. Now we're going to talk about the atmosphere, the third and sort of final sphere of the Earth system. Remember, we skipped the geosphere because we're not really concerned in this course with rocks. So let's get into it. So the atmosphere today. Okay, so the atmosphere, what's important to remember about the atmosphere is that it hasn't always been the same. That's sort of not how the atmosphere works. Wait, what? Yeah. That's not really how the atmosphere works. So the atmosphere today is composed mainly of three major gases. It's composed of nitrogen, about 78% of all the air that surrounds us in the atmosphere. Oh, also backtracking, the atmosphere is defined as the collection of gases and everything that happens within that gaseous, medium that surrounds the Earth. So, okay, back to the gases. 78% of all those gases are nitrogen. They're nitrogen molecules, N2, meaning two nitrogens bonded together. About 21% of all the air around you is oxygen. And then about 1% of it is argon. Now, in addition to those three major gases, there are several less commonly distributed, but still very important gases. And those are water vapor, carbon dioxide. Those include water vapor, carbon dioxide, methane, ozone, nitrous oxide, etc. Those are the big ones that we'll be thinking about and focusing on in this course. So if we present that as a pie chart, you can see that really the makeup of the atmosphere is dominated by nitrogen. Almost 80% of all the gas around you is nitrogen. Nitrogen in the atmosphere is considered inert, which means that it does not have any impact on your life, really. It doesn't influence climate change. It doesn't influence how you live, how you survive. It is important somewhat for plants, but it's a very complicated process, so that the atmospheric nitrogen is not directly a factor for plant growth, although plants do need nitrogen. The one small way in which you may experience, let's say, the nitrogen in the atmosphere is during a thunder and lightning storm. So lightning is actually the atmosphere and the molecules in the atmosphere cracking with great force. And the reason why it's so bright and hot and loud and dangerous is because the nitrogen in the atmosphere is actually two nitrogen molecules bonded together by three covalent bonds, sorry. And those bonds are really hard to break apart. That's why nitrogen is so inert. It doesn't have any reactions. It's just bonded to get two nitrogen atoms bonded together, minding its own fucking business. But during a lightning storm, those molecules actually are being ripped apart. That's what the lightning actually is the molecules of nitrogen in the atmosphere being ripped apart. And the act of that is so energetic that it releases light and also sound, thunder. And so that's probably the only time that you experience the nitrogen in the atmosphere. About 21% of the atmosphere is oxygen. You do experience that all the time. It's very necessary for life. You breathe it in every day, every second, every millisecond, whatever. So oxygen is super important. Argon is also inert. And then all these other gases, some of them are critical for our understanding of Earth's climate, like carbon dioxide and methane and nitrous oxide and ozone. And then some of them, like water vapor, are highly variable across the globe and are the direct cause, generally, of what we might consider weather, and in particular clouds and rain and that sort of thing. So that Earth's atmosphere now, as I mentioned a couple slides ago, is very different than what it used to be. It's always been changing. So when the planet was first formed, and there was a very early atmosphere around the planet, most of it was in the form of carbon dioxide, sulfur dioxide, and water vapor. And the reason for that is because back in the day, back when I was a child, just kidding, back in the day, billions and billions of years ago, there was no life on Earth, right, when Earth started. And Earth was just a hot, molten rock with lots of volcanic activity and lava and magma on the surface. And volcanoes, when they erupt, generally emit water, carbon dioxide, and sulfur dioxide. And so you can actually see, right, these are three major volcanoes that are active today. Kilauea, for example, on Hawaii, Momotombo, and Erdaale. And they're all on different sort of types of volcanic hotspots. But all of them release some combination of water vapor, carbon dioxide, sulfur dioxide. Most of the water vapor that was emitted by these volcanoes 4.5 billion years ago at the beginning of Earth became the oceans. Most of the sulfur dioxide ultimately fell out of the atmosphere and has contributed to sedimentation and erosion. And then most of the carbon dioxide in the billion years since Earth was formed has slowly been taken up by plant life. So our plant life on Earth, after 4.5 billion years, after 3.85 billion years of life on Earth, our plant life is sort of reached almost a maximum sort of amount, right? So there's like there's a certain amount of carbon dioxide that can exist in the atmosphere through the eruption of volcanoes and whatever, and the plants have essentially taken almost all of that out. Now there is a small sort of trace amount that remains in the atmosphere and cycles through the atmosphere and plants and rocks and other things. And that's what we'll talk about when we get into the carbon cycle, and that's really critical for understanding climate change. But in general, the atmosphere is not all carbon dioxide. It's a very small amount now, but in the past used to be mostly carbon dioxide. So, I want to ask you a question, and I'm not going to show you the answer until we meet. So I want you to write the answer down on a sheet of paper and come prepared to it for our discussion. And I'm going to ask, show of hands, whether it's A, B, or C. So, Mount Everest, the tallest mountain in the world, about 29,000 feet above sea level. The top of Mount Everest is referred to as the death zone. Is it called the death zone because it's too cold for humans to survive for more than a few hours? Is it called the death zone because there's less air at that altitude? Or is it called the death zone because the percentage of oxygen in the air decreases with altitude? Which one do you think? A, B, or C? Oops. So, and so I'll give you the answer when we meet. So I want to talk then about, I just realized that I actually think I have to tell you the answer now in order to go on with this lecture. So be honest and write down what you think it is, and then I will tell you now. So come prepared with that to class. I will tell you now that the correct answer is B. The correct answer is B. Probably most of you wrote C, super normal. Most people write C. I wouldn't fault you for writing C, but it's actually B. There's less air at that altitude. And this is a really important concept because with increasing altitude, as we go up in the atmosphere, gravity, right, the gravitational force being exerted by the large rock that is the Earth starts to decrease, and so you get less and less actual air. Most of the air that surrounds the Earth, that is contained within the atmosphere, is contained within the first 10 miles from the surface up through the atmosphere. So even though the atmosphere goes 50, 100 miles up, depending on where you decide the end is, where the top is, most, like 92% of all of the air in the atmosphere is contained within the first 10 miles. And actually, in the first 10 kilometers, or actually 5.5 kilometers, is where 50% of all the air in the atmosphere is. So 50% of all of the air in the atmosphere is contained within the first 5 to 10 kilometers. And you can see that on this picture right here, right? About 50% of the air is contained below about 5.5 kilometers, and about 90% of it is contained below about 10 miles or so. This side is miles, this side is kilometers. So as we go up through the atmosphere, the amount of air decreases, which is, we typically measure this as the air pressure. So the air pressure decreases. The air pressure is just the compressibility of air, right? It's how much air is on top of you pressing down. So as you go up in the atmosphere, the air pressure decreases. So the air pressure is maximum at the surface and minimized when you're at the top of the atmosphere. The air pressure decreases exponentially, we say. So you can see this exponential graph here. As we go from the surface up through the atmosphere, the air pressure is decreasing exponentially. This also translates to the air density decreasing exponentially as you go up through the atmosphere. The temperature, so that's the amount of air, right? The pressure, the amount of air that's in the atmosphere. Now let's talk about the temperature. The temperature doesn't have the same sort of uniform exponential decrease as we go up in the atmosphere. The temperature kind of bounces around. And so typically when we talk about the temperature of the atmosphere going from the surface up through, 50 to 100 miles, we use the temperature actually to define the structure of the atmosphere. And so let's start with the layer of atmosphere that's closest to the surface, and that is the troposphere. Tropo meaning well mixed. So the well mixed part of the atmosphere, meaning where all the gases are kind of mixed throughout. It's like if you're making Kool-Aid, right? And you have a glass of water, and then you pour the Kool-Aid powder in, and you stir it around, you mix it around, the whole thing becomes uniformly red. That's kind of the troposphere. It's uniformly well mixed. And the troposphere, which contains 80% of all the air in the atmosphere, right? So because the air is decreasing uniformly, the amount of air is decreasing uniformly exponentially as you go up, thinking just about the troposphere, that's 80% of all the air. It's the part that's closest to the surface of the Earth. It's the lowest 10 or 15 kilometers or so, right? So like 5 to 10 miles. And it's contained down here. You can see it on this graph. So if this is the surface, the troposphere is that first layer up from the surface, 80% of the mass, the first 10 kilometers or so. It's also where most of the weather events in the atmosphere occur. Most of them occur in the troposphere, and subsequently, because of this, and we'll go over this as we get further along in this lecture, in that layer, the temperature pretty uniformly decreases with altitude. Now, it's not always a perfect decrease, but taken as an average over the whole globe, in general, the temperature in the troposphere decreases as you go up from the surface. So it's very warm at the surface relatively to very cold at the top of the troposphere. The top of the troposphere is known as the tropopause, right here. So the tropopause, the top of the troposphere. As we go above the troposphere, things start to get less orderly. Okay? So the troposphere is where we're going to ultimately focus the rest of this lecture on, because that's where almost all the weather events, that's where all the things we care about as humans and as living beings, sentient beings on this planet, we care about the troposphere. We don't really care about these other ones as much, though we do care about the stratosphere. So the stratosphere is the next layer up from the troposphere. And the stratosphere is characterized not by decreasing temperature, but by increasing temperatures. So from the tropopause up to the stratopause, the temperature actually increases. Not decreases, but increases. So it decreases in the troposphere, increases in the stratosphere. And the reason for that is because in the stratosphere there's a layer in the stratosphere that's composed of what we call good ozone. It's ozone, but it's good ozone because we don't breathe it in. It doesn't affect us directly, right, our biology directly, but it does serve a very important purpose for the Earth. So the ozone in the stratosphere, which we call the ozone layer typically, is really good at absorbing incoming ultraviolet radiation from the sun. Okay, so the sun is emitting radiation. We'll get into this when we get into the radiation budget, but the sun is emitting lots of energetic radiation. Some of it's ultraviolet, most of it's visible, some of it is infrared, but the ultraviolet, the vast majority of the ultraviolet radiation is absorbed by ozone in the ozone layer of the stratosphere. This has two major impacts. One, that all that absorption of ultraviolet radiation increases the temperature of the surrounding atmosphere, which is why the temperature is going up in the stratosphere. And number two, it prevents that ultraviolet radiation from reaching the surface where it would kill us. So we evolved on a planet with low ultraviolet radiation specifically because of the existence of this ozone layer. So we evolved in this way to not be able to really tolerate UV light, and it's specifically because of all the ozone that's in the stratosphere. Above the stratosphere, we have the mesosphere, and the mesosphere is, there's very little actual air there, and so because of that, the temperature is generally decreasing with altitude, and by the time we get to the top of the mesosphere, a lot of people consider that to be the top of the atmosphere. There's very little actual air molecules. It's mostly just empty, dark space. But there are a few molecules of air that do exist above the mesosphere, and we call this portion of the atmosphere the thermosphere, which can extend very far out into space. Basically, anywhere that there's even one air molecule could be considered the thermosphere. And the thermosphere has highly variable temperature because of this. Temperature is measured as sort of how rapidly molecules are vibrating, right? And so if you have very few molecules, it's difficult to take an actual temperature measurement. But if you're just looking at the molecules that are in the thermosphere, when it's dark, they are very cold, almost inactive. And when it's bright, when the sun is on that side of the globe, they're super hot because they're much closer to the sun. So in general, the temperature throughout the thermosphere increases if it's the day and decreases dramatically if it's the night, kind of like if you were on Mars with less air. There's an important distinction to be made between weather, which is what happens kind of in the atmosphere, and climate, which is really what we're focused on in this course. And so we have to understand weather in the atmosphere first before we can really understand climate. So climate, this is kind of a very common phrase that climate scientists and people who study these types of things say. Climate is what you expect, weather is what you get. A lot of people don't understand this distinction. One of those people, of course, is the very conservative Republican senator from Oklahoma, Senator James Inhofe, who famously went outside during a Washington, D.C. blizzard, made a snowball, brought it back into the Senate chamber, and asked this question. I asked the chair, do you know what this is? It's a snowball. And the point he was making was that because it was snowing a lot in D.C., climate change must not be real. And this represents a fundamental misunderstanding of the difference between weather and climate. Misunderstanding, of course, here is being very gracious. I personally think the senator was misleading and knew what he was doing and did this deliberately. But either way, let's assume that he didn't. This is just a general misunderstanding of the difference and the distinction between weather, which is it's snowing outside, and climate, which is, in general, on average, the globe is warming. So another way of thinking about this is that weather is what's happening, right, outside. Climate is what you expect to be happening outside. So weather is for example, today when I'm recording this on, what is the date? October 5th, Monday, October 5th. The weather outside today is fairly nice. It's sunny and it's in the 60s. So I think most of us would say that this was a nice fall day, whatever that means. Thinking about the climate, however, today's weather with high temperatures in the mid 60s is also pretty close to the climate. This is what you might expect for this time of year. Now, if it were 80 degrees out on October 5th, then the weather wouldn't really match the climate. The weather would be above normal. It would be warmer than normal. And when we say normal, what we're actually referring to is the climate. So today the weather is pretty normal, meaning the weather matches the climate, which is what we expect to happen today. If it was snowing outside today, then the weather would be below normal, right? It would be colder than normal. It would be unusual because the climate is what we would expect, and that is not in line with what we would expect in Chicago on October 5th. So climate is typically the average of all the weather over a period of time. And in the United States, with the National Oceanic Atmospheric Administration and the National Weather Service, NWS, climate is defined as the average weather for the last 30 years. And so as we end 2020, we'll actually be creating a new climate for the U.S., which will extend from 1990, I think 1991 through 2020, right? Those 30 years will be defined as a climate. Right now, we've been operating with the climate being 1980 to 2010. It's complicated because the climate is changing, so these things change. If the climate wasn't changing, you would expect those averages to be the same, right? Which is why we continue to update them. So climate is the average of all the weather. The weather, conversely, is the state of the atmosphere at a given time and place. So it's like the temperature, the air pressure, the humidity, the cloudiness, the wind speed, etc. outside right now. Okay, at a single point in time. That's the weather. The climate is what you expect, the normal, right? The average. So your group work for today, for Monday, when we have class, is going to be comparing the weather to the climate for one of these American cities. And I will explain this in more detail when we meet on the Zoom. But this is, in general, what I'm going to want you to do. I'm going to change this, however, to September 2020. So don't start yet. I'll introduce this when we meet on the Zoom. So, moving along then, talking, so the rest of this lecture is going to be a focus on the weather, on what causes weather in the atmosphere. And then we're going to use that knowledge to then talk about, for the rest of the course, the climate. So the most important gas, right, despite it being very low abundance in the atmosphere, is water vapor. It tends to be the most abundant variable gas, meaning it's not nitrogen, it's not oxygen, and it's not argon, but of all the rest, it's usually the one that's in most abundance, unless you're in the Sahara Desert. We're talking about water vapor as a gas, okay? We're not talking about liquid drops of water. We're not talking about clouds. We're talking about vapor, invisible, gaseous water vapor. The source of this water vapor is through evaporation, okay, off of lakes, oceans, streams, etc. And the sink, meaning where it's taken up out of the atmosphere, is in condensation into clouds and then ultimately rain, which rains down onto the surface. It's the water cycle, right? So we're focusing on the gaseous part when it's a gas, an invisible gas in the atmosphere. So typically, on average, the concentration of water vapor is maximized near the surface in the tropics and decreases as you go up and as you go north or south towards the poles. Water vapor is a greenhouse gas. It's actually the most important greenhouse gas, and we're going to get into that in a second. And it also releases latent heat, okay, which we'll talk about in detail. which fuels weather systems. So without understanding water vapor, we can't understand weather, and without understanding weather, we can't understand climate. So we need all of these pieces together to really understand what climate change is. So let's review the phases of matter, because this is going to be important as we talk about water vapor. Especially, this lecture is broken into two parts because there's a lot of material, there's a lot of information. And so this is kind of an intro to that second part. So most matter, all matter, actually, can exist in three phases: as a solid, as a liquid, and as a gas. And if we're just talking about water, H2O, the gas version of water is water vapor. It's gaseous, it's clear, it's not steam. Steam is actually not a gas. Gas is invisible, you can't see it. It's just a gas. Just like there's probably water vapor in between my eyes and the camera on my computer right now. There's probably water vapor there. And actually that water vapor probably got there because it's evaporating from the droplets, the small droplets of water that are coming out of my mouth as I'm screaming at my computer. It's evaporating into the air, becoming a gas. Okay, liquid water, we understand that. Liquid water is liquid. It's also the water that forms clouds and rain and all those sorts of things. So that's all liquid water. And then solid water, of course, is ice. The processes that cause liquid water to become gas is called evaporation. The process that causes gas to become liquid is called condensation. Okay, and these terms will be very important. Evaporation, condensation. The process that transforms liquid water into solid water is freezing, and the process that transforms solid water into liquid water is melting. I think we all know this. Water can also go directly from ice to a gas in a process known as sublimation, and can also go from gas to ice in a process known as deposition. When these processes happen for water vapor, right? So if we're talking about, for example, evaporation, evaporating liquid water becoming a gas, that process requires energy from the surrounding atmosphere. Okay? So when we're going from a liquid to a gas, we require energy, which means that the atmosphere around that water is giving energy to the water, which is transitioning from liquid to gas. Which means that the atmosphere itself is getting cooler, actually, in response. When we condense water, when we go from liquid when we go from gas, laptop ran out of space as I was recording that, so I now have to finish this lecture in a subsequent follow-on recording. So anyway, we were talking about the energy that's needed to require these phase changes. So condensation, for example, which is going from gas to liquid, releases energy, which warms up the atmosphere around the water molecules. Evaporation, which is going from a liquid to a gas, requires energy from the surrounding air, so that actually cools the air around it. That's less common, for example, than condensation, which is the process of formation of clouds, for example. And that's the end, I guess, of this slideshow.